in 1,000 milliliters, you could do the density. There's 18 grams per milliliter, and et cetera, but what it comes down to is that in 1 liter, there's 55.5 ... moles of water. And at any given second, I find in textbooks, they say there's not much water that's in the protonated form. There's not much compared to 55. This is 55.5 times 6.02. 6.02 times 10 to the 23rd, which is a lot. So the proportion isn't high. But if we do the math here, it turns out to be 0.1230, 3 more zeros, 1 mole of water is in the protonated form. Now this still, mole, we know equals 6.02 times 10 to the 23rd. So if we do the math on this, what you see is 10 to the 23rd, if we count backwards, 23rd, 22nd, 21st, 20th, 19, 18, 17, 16, you're still talking, in 1 liter of water, there's roughly 10 to the 16th number of individual water molecules that at any given second are going to have an extra proton, and so I'll show an equal number that doesn't. So, you know, I would read the books and they're saying like, oh, there's very few, like there isn't that many. But 10 to the 16th in 1 liter is a lot. So the mathematics of how pH comes into this, because I think once the kids get the confidence that all we're counting is the number of protons in a solution of 1 liter, you know, it'll help to have a liter beaker there or something to do that. So counting decimal places is the whole trick to pH. So if we have this many mole at any given second, I tell the kids, algebra is your friend. I know you all hate math and everything else, but algebra makes things simpler. So the first thing we do, instead of having to write this out all the time, we already see that mole is representing Avogadro's number, so that makes it simpler. But writing this out becomes complicated. So the way the math would come in is we take the decimal point, and we just move it to make this full. So we go -1, -2, -3, -4, -5, -6, -7. So if we move that decimal point, I won't be concerned with significant digits here, but this becomes 1.0 times 10 to the -7. And bringing the mathematics into it, you know, when I started in algebra, there was always the concept of, well, how does 10 to the 0 equal 1? Because we're so used to anything with 0 either being undefined or being 0. This is where the math comes in, because you can't take the log of a negative number. You know, we all memorize that by words, and then we never know where the application comes in. But pH is where it comes in, because I tell the kids again, to even write this, I say, scientists, we're not lazy, but we like to condense things. So instead of even writing this, it's too much for us. So what we want to do is take the negative logarithm of that, which now brings, just dealing with the exponent, to be the power of hydrogen, pH, equals 7. So if you can work backwards through this, you'll know that the 7 is related to how many mole in 1 liter is protonated at any given second. So the mathematics behind this, which you can start doing little tricks with, to either give them confidence or make exercises, there's a whole bunch on the web there. I love to do this with graduate students sometimes. It's got a pH of 0. And you'd be surprised how many people go, that's impossible. You can't have a pH, because they're just so used to, you know, everything being. But a pH of 0, does everybody know what that exponent would be? Because it's, if we can work backwards again from the decimal point, we're thinking this way was 7, so we actually had to move the decimal point from where it was 1 times 10 to the -7 to 1, 2, 3, 4, 5, 6, 7 positive places, which means now instead of 1 times 10 to the -7 became 1 times 10 to the 0. It's -7 and 7 is 0. And this is where taking the negative log of that. So the mathematics can get complicated. And another one to say is, well, it's got a pH of, say, -1.8. And you're just not used to seeing it that way, but I'm hoping my memory serves me correctly. But this would be an 18 molar solution, wouldn't it? So an 18 molar solution of, say, hydrogen sulfuric acid should have a pH of negative 1.8 or negative 18.
That's pretty close.
Pretty close to
Yeah.
giving. But see how the mathematics, it's back to where that decimal point goes. And what we're thinking is the protonation of the water. But then what do the books do? We go right in, and the first notation they're showing is H3O plus, and it's not even another hydrogen. You know, I found the kids were getting confused with that. So that's why, again, I'll say it's H2OP plus. And then it's just a matter of manipulating where that decimal point goes in relation to where the 1 liter is. So how am I on time? I went through that real quick.
Well, you said you about 5 minutes.
Still have 5 minutes?
Yeah, 5 minutes.
The talk was based on the pH, so I hope I can just kind of diverge and show a little bit. I know you look at the water molecule and think, you know, oh, well, it looks like something in kindergarten, but it works with college because all the different diversities that water has, with MickeyMOLE, like I said, everybody would draw it as Mickey Mouse, not even with the eyes, but it's the electron pair hands. This is the way I grasped out how water was working. So if you draw it this way, what you can see is that in an aqueous solution, I ask kids, you know, what happens when you put salt in water, sodium chloride? They go, it disappears. And I go, no, it doesn't disappear, but what happens to it? It dissolves. And does it dissolve into sodium and chlorine? It dissolves into the ions. So what happens is you have a crystal, let's say the Na plus, NaCl, Na plus, Cl minus. So you get this kind of crystalline structure for the salt. But if you picture the water again, the negatives on water with the hands are going to grab onto either the chlorine or the sodium. And kids know just from the magnetic properties of water, negatives are going to look for something that's positive. So when salts dissolve in water, what happens is Mickey will grab sodium and pull it, and if you want to stress the octet, you know, chlorine is going to keep that extra electron, and sodium is going to give it up. So sodium gets pulled away in water by Mickey's hands. And then conversely, what will happen is now you've got the chlorine, it becomes chloride anion with a negative charge, so water's going to grab onto that by the ears. I guess the more I think about it, it's not that the water grabs onto the chlorine, it's more that the chlorine is going to grab onto the positive portion of the water. So, as I said, I could go on forever about water. Another thing I'll say is, I was in a graduate level neurobiology course, and at the cell membrane, I don't know how much biology, but I know most general chem students go on to study biology. At the cell membrane, there's a sodium-potassium pump that they talk about. Well, I was sitting there one day, and the teacher mentioned that sodium isn't able to cross the cell membrane wall, but potassium is free to come and go. And me being the only chemist there, you know, the biologist didn't want to think about chemistry. I said, wait a minute, potassium has a bigger ionic radius than sodium, so why would potassium be able to come and go across the cell membrane, but sodium can't? And his immediate response was the pump. And I said, well, but the pump is what works opposite to create the gradient. I don't know if you're all familiar with that, but they get a gradient. You get so much sodium on one side, and that's what causes the nerve conduction to go. Does anyone in the audience know why potassium is free to come and go and why sodium isn't? Ionic radius? And when they're hydrated, what happens is sodium, I don't know exactly, but sodium cation has a smaller ionic radius than a bigger potassium because it's got, I should write K, I guess.
K plus.
So with a bigger ionic radius, this is where physics comes into it, the sodium will be hydrated with a three-dimensional thing of water here. Three waters gives it a bigger radius in an aqueous solution. So this shows even in water that's not in your blood or somewhere, sodium is a bigger molecule because holding on to three waters, potassium can only hold two. This, you got to remember, is in three dimensions, and I won't draw the little ears from it. But I think it's easier for them to see that, you know, water, what's going to happen now, as I said, this is why I think the cartoon helps again. Mickey is going to grab onto Mimi's ear, you see how the hydrogen bonds can make water stick together. And the last thing that I'll say about water is, ask kids, why does ice expand? Why does ice expand, do we know? It's one of the only few molecules or anything in nature that as you cool it down actually expands. And the interesting things are, because if it didn't, then ice would be denser, lakes would freeze from the bottom up, and the fish would freeze and all that. The Mickey Mole comes in good again, because you get this kind of daisy chain thinking where he grabs onto her ear, she grabs onto his ear, and you get these little structures of like maybe about 6 waters. There's all different forms of ice. There's not just one kind. And you get this empty space in there. And then over here, it's kind of like a little benzene ring hexagons here. So you get all this empty space that makes water actually expand. And I think just the cartoon representation is a lot better than just leaving it to the student's mind of what water is, or drawing it without the electron pair of hands. So I guess that's about my time. Thanks. I know I shot through it.
Next speaker, is there any questions? Since we're all in possession of a handout, I didn't get any.
Yeah, I was going to say, on the web, there's all kinds of little fill-in-the-blank worksheets and more instructions on how to do it. So
Do we have a question while our next speaker is coming up?
I was just out for a moment at the beginning, and you using this in college level course, or I know you said you used it.
Well, in the college
schools and
level,
stuff.
I really go into the mathematics of it.
Yeah.
Then I can take my time with it. I know I shot through it because I wanted to cover a lot, but I started working backwards through, I thought it worked so good with community college, which is kind of the equivalent of honors high school. So I thought, well, I'll take it to high schools. The high school kids got it, senior, chemistries. Then I took it down to just general science in high school. And then I started working backwards with those 7th graders, like I said, Vallejo. Then 5th grade was my lowest one, and probably about 4 months ago, I did it with the 4th graders. And they have a blast with it, because they can draw, it's just numbers and letters, and you get them giggling and smiling about it. I think that's half the battle there. But as far as pH, if they get it in their mind